Hey everyone, I think we can get started. So today what I wanted to do is a sort of reaction vid to this recent talk that Andrei Karpathy gave at uh, CVPR, which is a computer vision conference. Um, and the reason so basically I saw a lot of people comment that this is an interesting talk, but I didn't necessarily see too many people summarize it or what was interesting about it. I think it had a bunch of interesting ideas around like what does it look like to build teams like ML teams like around something hard like self-driving cars, like which parts of the stack should you own. And actually what I really like about Karpathy is that even though like he is an extremely accomplished researcher, I think like as an ops and as a dev person he's also extremely talented and has like very unique perspectives. And so I thought, yeah, I mean, what we're gonna do today is I'm just gonna play this video, and I'll pause at various points. Like if you have any questions while this is happening, feel free to interrupt me. I'll answer. Otherwise, I'll just pause and start riffing on parts that I thought were interesting. So let's just go.
I'm embarrassed to say that I barely use Zoom. I know this is shocking.
Yes. It's a pleasure to introduce Andrei. I have to say, I think he doesn't really need a lot of introduction. But yeah, he is the senior director of AI at Tesla, and he basically supervises and leads the team responsible for all the neural networks in the autopilot. With this, it's a pleasure to have you here, and I'm really looking forward to your talk.
Yeah, great. Thank you for the introduction. And I'm very happy that I was able to display some impressive zero-shot learning on Zoom.
Okay. Just to not need an introduction anymore.
Yes, I'm very excited.
He speaks really fast, actually. Feels like he's on 2x.
I would like to talk a bit more about what Tesla has been up to over the last few months. So first to start, I guess we are here at the CVPR workshop on autonomous driving. So I think I'm preaching to the choir a little bit, but I'd like to start with some slides on like why we're doing all of this. And I think, unfortunately, we're kind of like in a bad shape when it comes to transportation in society. And basically the issue is that we have these metallic objects traveling incredibly quickly and with very high kinetic energy. And we are putting meat in the control loop into the system. And so this is quite undesirable. And really fundamentally what it comes down to is people are not very good at driving. They get into a lot of trouble and accidents. They don't want to drive. And also, in terms of economics, we are involving people in transportation. And of course, we'd like to automate transportation and really reap the benefits of that automation in society. So we all, I think, are on the same page that it should be possible to replace the meat computer with a silicon computer and get a lot of benefits out of it in terms of safety and convenience and economics. So in particular, silicon computers have significantly lower latencies. They have 360-degree situational awareness. They are fully attentive and never check their Instagram, and alleviate all of the issues that I presented. And so I think this is not super shocking, and a lot of people have been kind of really looking forward to this kind of a feature. This is a frame from iRobot, a really good movie if you haven't seen it. And here, Will Smith is about to drive a car manually. And this other person here is shocked that this is going to happen. This is ridiculous. Like, why would you actually have a human driving cars? And so I think this is not very far from truth. And this movie is taking place in 2035. So I think by then, I actually think this is a pretty prescient prediction. So what I think is kind of unique about Tesla and in our approach to autonomy is that we take a very incremental approach towards this problem. So in particular, we already have customers with the Autopilot package, and we have millions of cars, and the Autopilot software is always running and providing active safety features, and of course, the Autopilot functionality. So we provide additional safety and convenience to our customers today, and also the team is working on full self-driving ability. So I would briefly like to very quickly speak to the value today that we provide, just to give you some examples of what the team is up to and what we're sort of doing today. So here's an automatic emergency braking scenario. So the driver here is proceeding through an intersection, and you can see trouble coming here. So the person kind of crept up from here, and the car sees the pedestrian, object detection kicks in, and we slam on the brakes, and we avert collision. Here's an example of a traffic control warning. So this person is probably not paying attention, potentially on the phone, is not braking for the traffic lights ahead, but we see that these are relevant traffic lights. They are red, and we beep, and the person immediately starts slowing, and probably does not actually enter the intersection. These are examples
Uh,
from
yo,
parallel
hey, Andro,
mitigation.
MK1.
And
Thanks
here
for
a
popping
person
by.
is unparking
Yeah,
on
like
the
we're
driver's
watching
side,
this, and if you have any
and
questions,
they
let
are
me
trying
know.
to turn,
I
and then
wasn't
they mess
aware
up, and
that
they
like
accidentally
traffic
floor it.
control warning actually existed
So they floor it
in
right there,
Tesla
and
vehicles.
the
Kind of
system kicks
nuts.
in. It sees pedestrians ahead of us, and it slams on the brakes, and
I
it
guess
averts
depends how reliable. If
what
you
would be a
depend on
very
it, you
gnarly
could kill
situation in this
yourself
case.
easily. But I guess it's better than not
Here's
having
another
it.
last scenario I can show briefly. So this person is trying to park, and they turn to the right here, and they intend to press the brake, but they actually floor it. And the system again sees that there's no driving path forward and actually slams on the brakes and averts. In this case, this person is not going to be swimming in this river imminently. So these are some examples of the value that we are providing today in this incremental autonomy fashion. But of course, the team is actually sorry about that. The team is working primarily on the FSD functionality, which is our full self-driving suite. So here we have the FSD beta product, and it's in the hands of about 2,000 customers. And this is an example from one of the customers driving around San Francisco. And these people are posting videos on YouTube, so you can check out a lot of videos. But what we're showing here on the instrument cluster is we're showing all of our predictions. So you're seeing some road edges, some lines, some objects, and the car, of course, is navigating around autonomously here in San Francisco environment. Now, we, of course, drive this extensively as engineers, so it's actually fairly routine for us to have zero intervention drives, I would say, in like sparsely populated areas like Palo Alto and so on. I would say we definitely struggle a lot more in very adversarial environments like San Francisco. A lot of people working in autonomy, of course, know all about that as well. So this drive ends up being a fairly long drive, and it's zero interventions in this case. Now, one thing I like to point out always whenever I show the video of Tesla driving around autonomously in these city environments is you've seen this before, and you've seen it for a decade or more. So here's a Waymo taking a left at an intersection, and this is actually a pretty old video, I believe. And so you've been seeing stuff like this for a very long time. So what is the big deal? Why is this impressive? And so on. And I think the important thing to realize, and that I like to always stress, is that even though these two scenarios look the same, so there's a car taking a left at an intersection, under the hood, and in terms of the scalability of the system, things are incredibly different. So in particular, a lot of the competing approaches in the industry take this LiDAR plus HD map approach. And so the idea is that you take an expensive sensor, a LiDAR, on the top of the car, and it basically gives you range finding around the vehicle in 360 and gives you a point cloud. And what you have to do is you have to pre-map the environment with the LiDAR sensor, and you have to create a high definition map. And then you have to insert all of the lanes and how they connect and all the traffic lights and where they are. And you basically have to create a high definition map. And then at test time, you are simply localizing to that map to drive around. And so the approach we take is vision-based primarily. So everything that happens for the first time there in the car based on the videos from the 8 cameras that surround the car. And so we come to an intersection for the very first time. And
yeah, so just like to clarify some stuff, because I think he said quite a bit in this last section here. Let me draw this out for you. All right. So okay, so basically the old model. So let's just say old model. You basically have an HD map of the environment. So like imagine that you would get this via GPS, and then you also have LiDAR. And then you want to basically match these two things. And then what you want to do is localize yourself and then make decisions. Right? So the LiDAR is expensive. This is expensive. I'm not sure how expensive this matching operation is or the localized operation, but at a high level, this is the old model. Whereas like with the new model, you basically have like 8 video streams. So essentially 1, 2, 3, 4, 5, 6, 7, 8. And then you want to pop all of these, I'm assuming, to some sort of single neural network and then make a decision. So architecturally, this is a bit simpler, but let's just like look at some of the nuances here. I'm sort of guessing as to what the punchline is going to be.
And we have to figure out where are the lanes, how do they connect, where are the traffic lights, which ones are relevant, what traffic lights control what lanes. Everything is happening at that time on that car, and we don't have too much high definition sort of information at all. And this is actually a significantly more scalable approach, because if our product is on a scale of millions of customers on Earth, and so it's actually quite unscalable to actually collect, build, and maintain these high definition LiDAR maps. It would be incredibly expensive to keep this infrastructure up to date. And so we take the vision-based approach, which of course is much more difficult because you actually have to get neural networks that function incredibly well based on the videos. But once you actually get that to work, it's a general vision system.
All right. So yeah. So basically the issue here, so this is expensive and then this needs to be updated all the time. Right. So it's doubly expensive.
And can in principle be deployed anywhere on Earth. So that's really the problem that we are solving. Now, in terms of the cartoon diagram of a typical sensing suite of an autonomous vehicle, these are kind of like the typical sensors you would see. And as I mentioned, we do not use high definition maps and we do not use LiDAR. We only use video cameras. And in fact, the vision system that we have been building over the last few years has been getting so incredibly good that it's kind of leaving a lot of the other sensors in the dust. And so actually, the cameras are doing most of the heavy lifting in terms of the perception that you've seen in the car. And actually, it's gotten to the point that we are able to start removing some of the other sensors because they are just becoming these crutches that you start to not really need at all. So actually, 3 weeks ago, we started to ship cars that have no radar at all. So we deleted the radar, and we are driving on vision alone in these cars. And the reason we are doing this, I think, is well expressed by Elon in his tweet. He's saying, when radar and vision disagree, which one do you believe? Vision has much more precision, so better to double down on vision than do sensor fusion. And what he's referring to is basically, like, vision is getting to the point where the sensor is like 100x better than, say, radar. Then if you have a sensor that is dominating the other sensor and so much better, then the other sensor is actually starting to like really contribute. It's actually holding you back, and it's really starting to contribute noise to the former system. And so we are really doubling down on the vision-only approach. And actually in this talk, what I would like to primarily talk about is how we have achieved vision-only control without radar and how we have released this.
All right. So this is not the full picture, right? So then we have radar. So actually, maybe I'll draw it a bit differently. So you have a radar, then optometry, and then you basically aggregate. And then you make decisions. Yeah, I mean, this sort of makes sense. Like, as in, if the sensor is so bad that it's holding you back, like I can see that. I find it surprising, but if it's true, I mean, it is what it is.
Quite successfully so far to the fleet, and what it has sort of taken for us to do that. So here I wanted to show a video, basically showing what the input of the system is. So we have 8 cameras surround, and
Hey,
these are
appreciate the subscribe.
cameras, and we have 36 frames a second. And you can see that basically you can actually understand a lot about this environment from this input. It's extremely information rich. You're getting a huge amount of constraints, 8 million bits.
Oh, more.
Constraints.
Hey, thank you so much, folks. Appreciate it.
on
Cas9,
the surroundings.
Xenobyte, Offsec.
And so
Appreciate it.
it's incredibly information rich compared to any other sensor you may want to have in a car. And so this is the one that we're doubling down on, because this is ultimately where all the difficult sort of scene interpretation challenges lie. So we prefer to just
Oh, hey,
focus all of our
Spacelot. Nice to see you online.
development on this.
Thanks for
And
joining.
we're not wasting people working on the radar stack and the sensor fusion stack. We only have one team, the vision team.
So yeah, that's a good point. I think like, so it's really a cost point, right? So as in this LiDAR is expensive in of itself. This HD map is expensive to update. All of these sensors are expensive, but also the teams that have expertise in them is expensive. So basically a sensor price is a function of the sensor price, but also the team size, right? So just by simplifying like simplifying the stack simplifies your org, All right, and again, like the real like the reason why people go for more complex solutions is that like ultimately people are expecting them to be better. But if they're not, like obviously there's just like so many benefits to this. So let's just keep seeing
Now, typically,
if
when
the
we're
rest
talking
is
about vision,
sensible.
the reason people are squeamish about using vision is, and the sort of challenge that almost always is pointed out, is people are not certain if neural networks are able to do range finding or depth estimation of these objects. So obviously humans drive around with vision. So obviously our neural net is able to process visual input to understand the depth and velocity of all the objects around us. But the big question is, can our synthetic neural networks also do the same? And I think the answer to us internally over the last few months that we've worked on this is an unequivocal yes. And I'd like to sort of talk about that. So in particular, the radar API, or like what the radar really gives you, is it gives you a quite accurate depth and velocity measurement. It's a pretty direct measurement of the car ahead of you in very nominal situations. So here I'm showing a random image on the left, and you are seeing the depth, velocity, and acceleration reported by the radar stack for this car. And you can see that it's a bit wiggly on the velocity, so this is some kind of a stop and go scenario. Now, when radar has a good lock on the car in front of you, it's given incredibly good depth and velocity. But the problem with radar is like once in a while, at random, it will give you a dumb measurement and you will not know when that is. And so it's incredibly hard to fuse with vision in our experience. So it might suddenly see a spurious stationary object because of a manhole or because of a bridge, or crossing objects are not very well tracked, or oncoming objects are not very well tracked. And it ends up contributing noise. I'll go into more detail in a bit. But for our purposes, what we want to do right now is we want to match the quality of these predictions using vision alone. So the question is, how can you get a neural net to predict depth, velocity, acceleration directly and do it with a very high fidelity, matching that of radar? So the approach we're going to take, of course, is we're going to treat this as a supervised learning problem, and we need a massive data set of depth, velocity, acceleration on a lot of cars, and we're going to train a large enough neural network and do a very good job at that. That's the standard vanilla approach, and that actually works really well if you do it properly. So here's what it took. So the first component that you need is an incredibly good data set. So, and when I talk about a good data set, I believe it has to have three properties.
Okay, yes. So let's just briefly talk about this. Remember, like the supervised learning framework. Like essentially, if you have something like if you have something like a radar or sonar or whatever, then they can get you speed measurements accurately. So let's say this is radar or sonar or whatever. Right? But sometimes they give you spurious measurements. And the neural network way of doing this is to say, well, okay, well, I'm going to get a bunch of images, right? And I'm going to have like some cars in these images. Is this a car? Yeah, okay. This is a car, right? And then this is the road it's going on. And then you want to have some sort of estimate of the velocity, like as a label, right? So basically, the data set would look like this. So this is like, let's say, I don't know, 256 times 256 times 3 tensor. All right, so this is the image. And then the label that you're trying to predict is it's a regression problem, and you're trying to predict the speed, right? So, and maybe, you know, we could make it so that you predict the speed and acceleration. Right, so these are both like numeric values. And so if you have enough of these pairs, then you could essentially train a neural network that takes the composition of these two things, and then can figure out, like, from a new image, like what is the most likely speed and acceleration. So this is sort of like the standard supervised learning approach. And then the key is always, like, the devil's in the details here, as in you need a really large data set. And the advantage of companies like Tesla, well, given that they're one of the few car manufacturers that already have cars with 8 cameras that are sold everywhere, they've all been collecting this data already because they're so invested in this vision approach. And so there's an idea here, like, where, you know, like, let's say this is the number of cars you have. Let me do this. So basically, car sales increase the number of driving data, which increases, like, full self-driving cars, which would then potentially increase car sales, And then you have a feedback loop here, right? So remember, feedback loops are key because this means that um, because Tesla is the only one that created this feedback loop here, that means that if they get to a certain point where their self-driving car is better than everyone else, it's going to be very difficult for anyone to catch up. And this is sort of a very similar reasoning to why, like, let's say orgs like Bing always really struggled to be number one. It's just because it's not because, like, let's say the algorithms are worse. It's because they have less data, so inherently the experience is worse. And so because the experience is worse, less people come to it, and so you get a reverse feedback loop where instead people are going to go to Google instead of using Bing. So this is a super important thing to keep in mind. Like anytime you're building like a really an ML, like sort of like any ML startup, like the key is never the models. It's sort of this feedback loop. So this is something I say over and over again. So it's like make sure to commit this to memory.
That are critical. It has to be large in millions of examples. It needs to be clean. So in this case, we have to have a very clean source.
Yeah. So yeah. So here he's adding also depth. Like sure. Yeah.
And it must be
So
diverse.
so then in this case, like you're predicting like a vector of three values, and you know, like that's sort of part of what makes neural networks interesting is like there's no constraint on what your input and output data can look like, and so in any sort of data structure, like basically any tensor can represent the data structure, like whether it's a graph or an image or a bunch of values, and so this is sort of partly why it's so powerful. Like the supervised learning framework is so powerful, just because you can represent so many problems with it.
We're not just talking about a single, driving clip of going forward on a highway. We really have to get into the edge cases and mine all the difficult scenarios. And I'm going to show you some examples. And when you have a large, clean, diverse data set, and you train a large enough neural network on it, what I've seen in practice is, in the words of Ilya Sutskever, success is guaranteed. And so let me show you some examples of that. So first of all, how are we going to achieve this data set? So of course, we need to collect training data. The typical approach might be to use humans to annotate cars around us in 3 dimensions. What we found actually works really well is an auto-labeling approach. So it's not pure humans, just like annotating cars. It's an offline tracker, as we call it, and it's an auto-labeling process for collecting data at the scale that is necessary. So we need, again, millions of hard examples. So this is where the scale comes from, is that it's not labeled purely by humans, although humans are involved, it's labeled automatically. So here's an example of some automatic labels we were able to derive for cars on the highway. And the way you do this is, because you are offline and you are trying to just annotate a clip, you have a large number of benefits that you don't typically have if you're at test time under strict latency requirements in the car. So you can take your time to fully figure out exactly all the objects and where they are. You can use neural networks that are extremely heavy. They are not deployable for various reasons. You can use benefit of hindsight because you know the future, not just the past. You can use all kinds of expensive offline optimization and tracking techniques. You can use extra sensors. In this case, for example, actually radar was one of the sensors that we used for the auto labeling. But there's actually a massive difference between using radar at test time and using it in the offline tracker. And that is that at test time, a radar can just report a stationary track immediately in front of you, and you have 20 milliseconds to decide if you're going to brake or not. If you're offline, you have the benefit of hindsight, and so you can do a much better job of calmly fusing if you really want to.
Okay, this is such an important point, by the way. So really the thing is it's not necessarily that they're not using radar, it's that they're not using it at test time because of latency requirements and because they introduce a lot of noise. And also, like, I mean, again, if you go back to this framework here, like the supervised learning framework, which is like you have the images, then you have this vector that you're trying to predict. Well, sure, you could get human annotators to do it, but it's very challenging. And so it's just like not scalable over like billions of frames of video generated every day or whatever. And so they take a sort of self-supervised learning approach, like very similar to techniques like BERT, which will mask out certain words and use that as a label for the word that's there instead of like using actual labels. So this is a very similar approach. And you could also sort of have various algorithms that can learn these labels either by looking at the future to better predict things or by fusing other sensors. But all of this is offline. So you're just basically have offline a data generating process that's building like a data set on which you fine tune your models, and then you deploy something entirely different at test time. So this is, I think, a very valuable insight.
And so there is a massive difference there. And in addition, you can of course involve humans, and they can do cleaning, verification, editing, and so on. And so we basically found that this was a massive lever to allow us to reach the scale and the labeling quality. And then to get the diversity, that was also a massive fight. So here's some examples of really tricky scenarios. So here there's some, I don't actually know exactly what this is, but basically this car drops a bunch of debris on us, and we maintain a consistent track for the label. And of course, if you have millions of labels like this, the neural net, if it's a powerful enough neural net, will actually end up learning to persist these tracks in these kinds of scenarios. Here's another example. There's a car in front of us, and I actually am not 100% sure what happens in this case, but as you'll see, there's some kind of a dust cloud that develops here and briefly occludes the car. But in the auto-labeling tool, we are able to persist this track because we saw it before and we saw it after, so we can actually stitch it up and use it as a training set for the neural net. Here's one more example of an adversarial scenario from heavy snow. Again, we can auto-label this fine and create a large collection of examples. Now, as we were working on this over a duration of, I want to say, of roughly 4 months of really just focusing a lot of the team on this problem of achieving really good depth, velocity, and acceleration, we've ended up developing 221 triggers manually that we were using to source data from our customer fleet. And this is just an example, some examples of the 221 triggers that were used to collect all of these diverse scenarios. So for example, we have shadow mode, where we deploy a neural network that is pretty good at predicting depth and velocity. And what we do is we run it silently in the cars of our customers, but it's not actually connected to control. What's driving is the legacy stack. But we're basically running the new measurements of depth and velocity, and we're, for example, looking at whether or not they agree or disagree with the legacy stack or with the radar. We're looking for other sources of jank, like for example, if there's bounding box jitter, detection jitter, the main and the narrow camera disagree.
Oh, I see. This is an interesting point, by the way. Basically, so like while the car is driving, right? So say this is the car from the top, and then you have like these sensors. You can basically run n models concurrently. Have one main model make decisions, and then the n-1 remaining can look for disagreements, right? So
we predict that there's a harshly decelerating object, but the person seems to not mind. All kinds of disagreements between different neural network signals. And there's a long list here. It took us a while to actually perfect these triggers, and all of them are iteration, and you're looking at what's coming back, you're tuning your trigger, and you're sourcing data from all these scenarios. So basically over the last 4 months, we've done quite extensive data engine. We've ended up doing 7 shadow modes and 7 loops around this data engine here, where on the top right is where you begin. You have some seed data set. You train your neural network on your data set, and you deploy the neural network in the customer cars in shadow mode. And the network is silently making predictions. And then you have to have some mechanisms for sourcing inaccuracies of the neural net. So you're just looking at its predictions. And then you're using one of these triggers, like I described.
oh, so basically, and remain looking models for disagreements with both the main model and the driver, right? Just because, like, so this is like the driver is also a source of self-supervised learning.
You're getting these scenarios where the network is probably misbehaving. Some of those clips end up going to unit tests to make sure that we, even if we're failing right now, we make sure we pass later. And in addition, those examples are being auto-labeled and incorporated into a training set. And then as a asynchronous process, we're also always data cleaning the current training set. And so we spin this loop over and over again until the network basically becomes incredibly good. So in total, we've done 7 rounds of shadow mode for this release. We've accumulated 1 million extremely hard, diverse clips. And these are videos. So these are, you should roughly think about, say, 10-second clips, 36 FPS, something like that. In total, we have about 6 billion objects labeled cleanly for depth and velocity. And this takes up roughly 1.5 petabytes of storage. So that gives us a really good data set. Of course, that by itself does not suffice. So we have an incredibly good AI team that is designing the neural network architecture that is basically the layout of the synthetic visual cortex in order to efficiently process this information. So our architecture roughly looks like this. We have these images coming from multiple cameras on the top. All of them are processed by an image extractor, like a backbone, like think ResNet kind of style. Then there's a multicam fusion that fuses the information from all the 8 views. And this is a kind of a transformer that we use to fuse this information. And then we fuse information first across all the cameras and then across all of time. And that is also done either by a transformer, by a recurrent neural network, or just by 3-dimensional convolution.
Okay, let's just quickly discuss the architecture. Because so this is what I initially drew. And the key is well, how do you combine all of these things? Well, then this is some sort of transformer. But then how do you extract image features? Well, you have something like a CNN. So this is the image, right? But then not only do you fuse across the images, you also fuse across time. So then this also takes in, so let's say this is image 1, image 2, right? So you're giving it image 1, like basically 1 to time t, right? So then you have a like you have 2-dimensional vector of total images that you're giving, like all like the 8 sensors. So it's basically 8 by t, so basically the time range times the dimensionality of the images. So let's say 256 times 256 times 3. So this is the total size of the vector that you're feeding your giga transformer.
We've experimented with a lot of kind of fusion strategies here to get this to work really well. And then what we have afterwards, after the fusion is done, is we have this branching structure that doesn't just consist of heads, but actually we've expanded this over the last year or so, where you now have heads that branch into trunks that branch into terminals. So there's a lot of branching structure. And the reason you want this branching structure is because there's a huge amount of outputs that you're interested in, and you can't afford to have a single neural network for every one of the individual outputs. You have to, of course, amortize the forward pass for efficient inference at this time. And so there's a lot of feature sharing here. The other nice benefit of the branching structure is that it decouples at the terminals, it decouples all these signals. So if I am someone working on velocity for a particular object type or something like that, I have a small piece of neural network that I can actually fine tune without touching any of the other signals. And so I can work in isolation to some extent and actually get something to work.
Okay, right. So then, but then this is like basically before this makes a decision, this is going to output a whole bunch of stuff. Like it's going to output, for example, a depth. It's going to output velocity, acceleration. And then these guys are each their own team. So changes are localized, right? So this is sort of like, because think about it, right? So let's say you come in and you're like, okay, well, like my accelerator model isn't working very well. So let me change like this thing. Well, your changes like may improve yours, but they may negatively impact your peers. So it becomes like this like hard discussion around like, well, what's more important? And instead, like by branching them out, you give each team their own incentive to improve their model, depending on their own expertise.
Work pretty well. And then once in a while, so basically the iteration scheme is that a lot of people are fine tuning, and once in a while we do an uprev of all of the backbone end to end. And so it's a very interesting sort of mechanism because we have a team of roughly 20 people who are, I would say, training neural networks full time, and they're all cooperating on the single neural net. And so what is the workflow by which you do that is pretty fascinating and continues to be a challenge to actually design efficiently. So we have a neural network architecture, we have a data set. Now, training these neural networks, like I mentioned, this is a 1.5 petabyte data set, requires a huge amount of compute. So I wanted to briefly give a plug to this insane supercomputer that we are building and using now. For us, computer vision is the bread and butter of what we do and what enables the autopilot. And for that to work really well, you need a massive data set. We get that from the fleet, but you also need to train massive neural nets and experiment a lot. So we've invested a lot into the compute. In this case, we have here a data set. We have a cluster that we're just building that is 720 nodes of 8x A100s of the 80 gigabyte version. So this is a massive supercomputer. I actually believe that in terms of flops, this is roughly number 5 supercomputer in the world. So this is actually a fairly significant computer here. We have 10 petabytes of hot tier NVMe storage, and it's also an incredibly fast storage. So I believe 1.6 terabytes per second. This is one of the world's fastest file systems. And we have also a very efficient fabric that connects all of this. Because of course, if you're doing distributed training across your nodes, you need your gradients to be synchronized very efficiently. And of course, we are reading all of these videos from the file system, and that requires really fat byte as well. So this is a pretty
Okay, interesting. Like so basically part of like so to answer the question, like, well, why did Tesla like why does Tesla have their own data center? Well, to me, it seems like there's two main reasons. So the first one is they want the basically the time for all syncs. So basically, the time it takes to sync data parallel training to go down. But they also care about efficiently reading video from disk. So I don't know for like how much they actually had to build some manual stuff here, because like I think NVIDIA had a tech called like NVLink that does a lot of this stuff. And so what NVLink does, it gives you like basically like it's a faster protocol than PCIe, because PCIe will involve you talking to the host. First, you have to talk to a CPU, and then the CPU lets you talk to another GPU. So basically, the communication would look like this. So GPU 1 talks to CPU, which talks to GPU 2. And then they have to keep doing this. Whereas with NVLink, you can imagine a more like mesh-like structure where GPU 1, 2, 3, 4, for example, can all talk to each other. Did I do all the... like they can all talk to each other. So obviously like this is a lot faster, and it's really just dependent, like, so this is via PCIe, like PCIe, and this is each like an NVLink chain. So this is on the first point. And then on the second point, like, remember, so GPUs are initially designed for graphics. So it's actually very important for them to be able to render video assets very quickly. So let's say you're watching like a really high quality movie, or if you have like some like texture data that you quickly want to be able, like these large like multi-gigabyte textures that you quickly want to render on the screen. So this is basically the bread and butter of GPUs. Like GPUs are great at video decoding, you know, because of video games. So this is kind of an interesting point. And so you'll notice like a lot of like accelerators nowadays to deal with distributed training have this sort of structure. So you want to, as much as possible, avoid having to send stuff back and forth to the host, because otherwise you just experience these massive slowdowns.
pretty incredible supercomputer. So this is a GPU cluster. Next up, we're really hoping that we're currently working on Project Dojo, which will take this to next level, but I'm not ready to sort of reveal any more details about that at this point. What I would like to do is I would like to just briefly plug the supercomputing team. They've been growing a lot. And so if high-performance computing for this application and for training these crazy neural networks excites you, then we would definitely appreciate more help. So please contact the supercomputing team at supercomputing at Tesla to help us build these clusters. On the left here, we have the compute nodes, and on the right, this is a network switch, actually. So the wires here is kind of like the white matter of this synthetic cortex, I guess. The other thing I wanted to briefly talk about is I wanted to also mention briefly that this effort basically is incredibly vertically integrated in the AI team. So as I showed you, we own the vehicle and the sensing, and we source our own data, and we annotate our own data, and we train in our on-prem cluster, and then we deploy all of the neural networks that we train on our in-house developed chip. So we have the FSD computer here that has 2 SoCs, FSD chips here, and they have our own custom NPU neural processing unit here at roughly 36 TOPS each. And
okay, yeah, so notice here they're basically talking about int8 quantization. Graph optimization in Fusion, almost everyone does this. So like the classical example is, well, let's say you're doing, let's just talk briefly about this. So basically custom hardware. So there's a few key ideas. Like one is you optimize for what you care about, right? So typically for each different kind of bit of precision, you would need like your own adder units. And so if all you care about is 8-int precision, and then you can get really good high throughput with that. So for example, NVIDIA does 16-bit with their tensor cores. And so here they're talking about 8-int precision. Obviously, that's a lot, like a lot less data than floating point 16 or floating point 32. But if it works, right? And then what else? So they also talk about flops. Like I forget like how like I forget how to compare this to something like a GPU. But basically flops is kind of like flops per dollar is really the only thing that matters in hardware. And then let's see, what else do they do? So yeah, so here they also talk about having SRAM. So the idea is SRAM uh, is gonna be more expensive, but it's faster. But in this case, like, if you just like need one of these chips or two or whatever per car, it's not like a huge deal.
So these
You can also have like basically, let's see, so threshold calibration. Okay, so for this 8-bit precision, you could have your own custom compiler. So remember, like, let's say you're doing something like writing a PyTorch model, and this PyTorch model assumes like 32-bit. Then you could make it go through like the Tesla compiler, and then it becomes like 8-int precision, and it works just fine. The other thing to keep in mind is graph optimization and fusion. And this sounds like a complicated concept, but it just goes to show you how simple ML compilers still are. So let's say you're doing like an operation, like you're doing, like I don't know, like you have like layer, and then you're doing a CNN on X, and then you're basically doing a uh, relu out on the layer. So for example, you're doing like relu of layer, right? And so how does this actually work, right? So the way this works is, well, you're gonna like, let's do it step by step. It'll be more obvious. So I know this sounds really trivial, but it's actually an interesting point I learned recently. So first off, like you're gonna have X, right? So X is gonna be like on disk. So from disk to RAM. Right, so you're doing a read. So we're doing a read. And then we're going to apply a CNN. So for the CNN, that means we're going to do now a write, where we're going to basically write the output of layer back to RAM, or back to disk as well. But then in the relu out, what you're then doing is you're doing another read, where you're saying, okay, I want to get the output of layer. Let's say, so I want to read layer from disk and to RAM and back to RAM, and then now I want to write back the output, right? So now I want to write relu out from yeah. So I want to write relu out back to RAM and disk. So the idea behind something like operator, so you can imagine this is like totally pointless. And so the idea behind things like operator fusing is that we skip this step. So here, so you're reading this, and you basically skip this step. So you're skipping an independent operation. You now have a joint operation called CNN. I mean, let's call this like a conv2d. Sorry, it's a bit more descriptive. So now, like, if we have a conv2d followed by a relu in our computational graph, the compiler will come in and will fuse this into a single operation called the conv relu with the following semantics, right? Because you don't want to go change the source code for everything. You just want to do a graph level transformation, introduce your own operator, and you're off to the horses.
Designed for the neural networks that we want to run for FSD applications. And so everything is very vertically integrated in a team. And I think that's pretty incredible because you get to really co-design and engineer at all the layers of that stack. And there's no third party that is holding you back. You're fully in charge of your own destiny, which I think is incredibly unique and very exciting. And then we have a deployment pipeline here where we take these neural networks and we do a lot of typical graph optimization, fusion, quantization, threshold calibration, and so on, and deploy it on our chip.
Yes. So fusion is what I just said. Threshold calibration is like if you have gradients that are too small or too big, you just like clip them. So gradient clipping is a so I talk a bunch about this in the deep speed video. So if you're interested in a lot of these graph level optimizations, I also have a series on ML compilers, so you can go check that out. And then let's see, so like optimization, fusion, yeah, and then like automatic quantization is turning things to 8-bit automatically.
Networks run there. So now what I'd like to show is, I first would like to show some qualitative examples of some of our results in terms of the depth and velocity predictions that we were able to achieve by putting all of these pieces together and training these networks at scale. So the first example here, I have a video where this is on track testing. So this is an engineering car, and we asked it to slam on the brakes as hard as it possibly can. So this is a very harsh braking here in front of us. Even though it doesn't look like that in the video, this is very harsh braking. So what you can see on the right here is you can see the outputs from the legacy stack, which had radar vision fusion, and from the new stack, which is vision alone in blue. So in the orange legacy stack, you can actually see these track drops here when the car was braking really harshly. And basically the issue is that the braking was so harsh that the radar stack that we have actually ended up not associating the car and dropping the track and then reinitializing it all the time. And so it's as if the vehicle disappeared and reappeared like 6 times during the period of this braking. And so this created a bunch of artifacts here, but we see that the new stack in blue is actually not subject to this behavior at all. It just gives a clean signal. In fact, here, there's no smoothing, I believe, on the blue signal here. This is the raw depth and velocity that comes out from the neural net, the final neural net that we released with about 3 weeks ago. And you can see that it's fairly smooth here. And of course, you could go into the radar stack and you could adjust the hyperparameters of the tracker, like why is it dropping tracks and so on. But then you are spending engineering efforts and focus on a stack that is like not really barking up the right tree. And so it's better to, again, just focus on the vision and make it work really well. And we see that it is much more robust when you train it at scale than something like this. Here's another example, fairly infamous example of slowdowns when there are cars going below a bridge. The issue here, again, is that the radar does not have too much vertical resolution. So radar reports a stationary object in front of you. It's as if like the radar doesn't know that there's like a stationary car in front of you or if it's the bridge above. It cannot differentiate those two.
That seems like kind of a big weakness of radars, right? I had no idea they can't see what's above you.
So radar thinks that there might be something stationary in front, and it's just like looking for something in vision to tell it that it might be correct, and then we create a stationary target and brake. And so in this case, in the legacy vision predictions, which were already producing depth and velocity, but because we were using radar, the vision inaccuracies were being masked because your bar is only at radar association. Your bar is not at actual driving. And so the depth and velocity were not held up to a high enough bar. And so basically what happens is vision reports for a few frames, reports a slightly too negative velocity for the car. And then it associates to the stationary object. And the stack is like, oh, that must be the stationary thing. And then we brake. And so this, of course, is much cleaner. And you see that the new stack does not see this at all. And there's no slowdowns in this case. Because we just get the correct depth and velocity, and vision obviously has the vertical resolution to differentiate a bridge from a car and whether or not the car is slowing or not. So again, you could go into the vision the radar stack or the sensor fusion stack, and if you have an improved depth and velocity, you could change the fusion strategy. But again, you're just kind of like doing dead work. Like this signal is so good by itself. Why would you do that? So in this setting now, we've improved the situation quite a lot. Here's another last example. We have a stationary approach. Again, this is in track testing environment. This is an example of a test that we would run. And we are just approaching this vehicle and hoping to stop. What you see in orange in the legacy stack is that it actually takes us quite a bit of time for us to start slowing. And basically what's happening here is that the radar is very trigger happy and it sees all these false stationary objects everywhere. Like everything that like sticks out is a stationary target. And radar by itself doesn't know what actually is a stationary car and what isn't. So it's waiting for vision to associate with it. And vision, if it's not held up to a high enough bar, is noisy and contributes sort of error. And the sensor fusion stack just kind of like picks it up too late. And so again, you could fix all that, even though it's a very gross system with a lot of if statements and so on, because the sensor fusion is complicated because the error modes for vision and radar are quite different. But here, when we just work with vision alone and we take out the radar, vision recognizes this object very early, gives the correct depth and velocity, and there's no issues. So we actually get an initial slowdown much earlier, and we've really simplified the stack a lot, and as well. So just speaking very briefly to the release and validation, we've extensively validated this before we, of course, ship this to customers. Just some example numbers for the validation itself. We've handpicked about 6,000 clips in about 70 categories of scenarios, like harsh braking, crossing vehicles, different vehicle types, environments, and so on. And we run these tests on all the commits of the build, and we run them also every day periodically as we were trying to drive up the performance on these clips. We also use simulation extensively for validation. We've also used simulation for training, although I haven't gone into that, but we've had some successes there. But we use it primarily for validation at this stage. And that's, again, diversity of scenarios, trying to make sure that the stack is performing correctly. We've done a lot of track testing, and I've shown you some examples of that. We've driven this extensively in the QA fleet, and we've also deployed this in shadow modes and seen that this stack performs fairly well. So in particular, for example, for the automatic emergency braking, we actually see a higher precision and recall compared to the legacy stack that is a fusion stack. And so having seen all this, we've actually released this. We've accumulated about 15 million miles so far, and 1.7 million of those have been on autopilot, and so far there have been no crashes. Now, of course, we're running at massive scale here, and so we do expect some crashes at some point. The legacy stack has a crash roughly every 5 million miles or so, I believe. And so we do expect some incidents at some point, but the improvements for the vision stack are not sort of stopping. So I think we're very confident that we're barking up the right tree here, and that we can actually get this to work really incredibly well. I also wanted to briefly give a shout out to auto labeling as an incredibly powerful method for sourcing training data. So we're applying auto labeling to all of the FSD tasks, not just to depth and velocity of the car in front of us. Here's an auto labeler for pedestrians. You can see that the tracks are very smooth. And this is, again, a completely offline process that we are applying not just to objects, but also to a lot of static environments. So this is some example of a 3D reconstruction. So here we see a clip, and this is a vision-only estimate of the depths of all the points. And of course, you don't actually want to really deploy these measurements directly into a car because they are too raw. So what you actually want to do is you want to...
I see. So it's really... And then you basically have a legacy stack. So auto labeling. And then this feeds into SSL, and then this is the legacy stack. And then this is the new stack, the vision stack.
Again, auto label. And you want to really think about what is the information I really need at test time in the car, and what is as close as possible to action, right? So you want to do all this work at training time, figure out exactly what happened in the clip, reconstruct the entire environment, and then you want to actually post-process the curb at training time. So you want to do as much at training time and labeling time as possible. And then you want to figure out what are the tasks I really need at test time. And that's the thing that happens in the car, subject to very strict latency requirements. You want to do as little post-processing there as possible. So we see that this is a very powerful lever on creating data sets. So in summary, what I try to argue and give you a sense of is vision alone is actually, is our finding that this is perfectly capable of depth sensing. It is an incredibly rich sensor in terms of bandwidth of information. And doing this and matching radar performance and depth and velocity is incredibly hard. I believe it requires the fleet because the data set that we were able to achieve was critical in all these performance improvements. And if you do not have the fleet, I'm not 100% sure how you can source all the difficult and diverse scenarios that we did source. Because I believe that
Yo, Pseudomate, how's it going?
So it's hard, it requires massive networks, a supercomputer, and
we'll be summarizing soon. The talk is almost done.
But all of these components are coming together in
It's
in a
like,
vertically integrated
well,
fashion
I would expect
as
some of these would
Tesla
be
AI.
questions because it looks like
And I
this
believe
last
that this
slide.
makes us sort of uniquely positioned in the industry where we are barking up the right tree, and we have all the puzzle pieces to make this work. And so if you are excited about this approach that we're taking and the networks and the work that we're doing, then I would encourage you to please apply and join the team and help us make this a reality. So you can go to tesla.com/autopilotai.
So I like this. So there's, for me at least, a few. Actually, no. Let me start writing down. So I think one, there's like some ideas around ML team organization where new kinds of data require more people. And submodularize models with common like dependencies and trunks. So teams can benefit from each other. There's two, I think this may be 2 points. There's like own your own stack. Own your own stack. You're not like you're not at the mercy of salesmen. And then 3, like basically the virtuous SSL feedback loop. I think I'll do a tweet summary after this because I think this was interesting.
It's a very simple process. You upload a resume and you have a blurb about some of the things that you've done that are impressive, and then that comes directly to us. And we'd love to work with you to make this a reality. Thank you.
Thanks for this very, very interesting talk. We actually got quite some questions. Since we are already over time, I will limit it to a few. We are at the kind of nice point at the end of the workshop, so you are a bit of a rough spot that you have to answer more questions than maybe other speakers. And kind of, I would like to go as a first one into the, kind of the maybe a bit to auto labeling, but actually the thing which really is necessary for the auto labeling, and this is these, this definition of these triggers.
Yep.
Did you ever try to investigate if you can automatically generate those triggers?
That's an interesting question. So the triggers are kind of like, they're designed based on what we're seeing and what's coming back in the telemetry from the cars. So we are seeing clips where maybe we didn't brake, but the person did, or vice versa. There's all kinds of disagreements with like human driving and the legacy stack. And we're looking at this, and typically we try to have signals of various generality. So for example, like a vision radar disagreement is a very general trigger. It can source all the disagreements. And then there are very specific ones, like maybe we struggled actually for a while when we were entering tunnels and exiting tunnels because there was a lot of brightness variation. So we struggled a lot there as an example. And we had to specifically design some triggers for that because we were not catching it with a high enough frequency. Because for any of these situations, you actually need to make sure they're represented well in the training set. So for us, this was a fairly manual process, but we do have a team basically dedicated to doing this full time, and they did this for 4 months. So I don't, like, how do you automate this? I think is a very tricky scenario because, again, you can have these general triggers, but I think they will not correctly represent the error modes. And I think it would be really hard to, for example, automatically somehow have a trigger that triggers for entering and exiting tunnels. That's something semantic that you as a person have to like intuit that this is a challenge for whatever reason and actually go after it specifically. So yeah, it's not clear how that would work, but I think it's a really interesting idea.
Yeah, so, I thought it sounded very interesting. The question sounded very interesting and not easy to answer.
Yeah.
Maybe another one which actually in somehow, let's say, 2 version showed up a bit was kind of in your vision only approach. Kind of could there be other sensor like, for example, thermal image
in the visible light spectrum. And I would say also that
with this, I would actually like to give some kind of concluding remarks on the workshop, or better.
All right. Okay. This was great. So I think this was it. Like, I'll write a tweet level summary, but in case like you just wanted to watch this part, what I found really interesting about this talk is there's sort of key ideas. I think like one is how to design ML orgs where like models have dependencies on top of each other, in such a way that people can benefit from each other, but also, um, but but also like build independently. The other is that like owning your own stack means that you're not at the mercy of a bunch of salesmen. Like you don't have to go beg Nvidia for GPUs, or let's say like you have to go negotiate with someone. Like you just have your own stuff, your own destiny. You can figure out how to plug and play, or how to change everything, or how to manage like the file system without asking for anyone's permission. And I think the last part is like more of like the business perspective, which is like this feedback loop of car sales, increase giving you driving data, which then you label with self-supervised learning, which gives you like driving data, which gives you better ways to self-supervise data, which then also improves your self-driving car capability, which then improves your car sales. I think this is so key, like pretty much for any business. Like here, so whether it's like let's say so auto labeling, so they're using legacy stack, uh, or like yeah, so legacy stack or driver data, uh, right? Then you also have like shadow models. So I think this is a really cool story actually. So and all of these probably let's see. Um, I mean yeah, so no, we already gave it driving data, so I don't think we need this point. And shadow models, I think, is sort of captured by like so SSL plus maybe I'll say uh, plus shadow models. So yeah, I mean this was a great talk. Actually, I felt like I learned a ton. I hope you enjoyed it. If you have any questions, feel free feel free to let me know. Otherwise, I think I'll start writing the tweet. And I am working on an article on ML ops. It's taking me longer than I thought it would. It's like there's kind of like more involved in writing the article than I expected. So stay tuned for that if you're interested. And if this was interesting to you, like make sure to subscribe, whether it's here on Twitch, YouTube, where I'm going to archive this video, and then Substack, where I'm going to be writing the ML Ops article. And thank you so much, everyone. Really appreciate it. Thank you for taking the time to watch me.